Hello everyone, and welcome to the Principal Component Analysis lecture. If you want a more mathematical background and a deeper dive into Principal Component Analysis, go ahead and read section 10.2 of an Introduction to Statistical Learning. Now let's discuss the basic idea behind Principal Component Analysis, or PCA. PCA is an unsupervised statistical technique used to examine the interrelations among a set of variables in order to identify the underlying structure of those variables. It is also known sometimes as a general factor analysis. Where regression determines a line of best fit to a dataset, factor analysis determines several orthogonal lines of best fit to the dataset. Orthogonal just means at right angles, and actually those lines are perpendicular to each other in the n-dimensional space, where the n-dimensional space is the variable sample space. There are as many dimensions as there are variables. So in a dataset with 4 variables, the sample space is 4-dimensional. Let's go ahead and see an example. Here we have some data plotted along 2 features, x and y, and we went ahead and put a regression line of best fit. What we can do now is add an orthogonal line, which is just at a right angle to that first line. And now we can begin to understand the components of our dataset. Components are a linear transformation that chooses a variable system for the dataset such that the greatest variance of the dataset comes to lie on the first axis, and then likewise, the second greatest variance on the second axis, and so on. And this process allows us to reduce the number of variables used in an analysis. And if we look back at our figure, we can see that that first principal line explains the 70% of the variation, and then the line orthogonal to that explains 28% of the variation. And right now we have 2% of the variation remaining unexplained. And note that the components are uncorrelated, since in the sample space they are orthogonal to each other, or at direct right angles. And we can continue this analysis into higher dimensions. Here we now have 3 components. Component 1, that principal component explaining most of the variance, and then component 2 and component 3 in a higher dimension as we go into the z-axes. If we use this technique on a dataset with a large number of variables, we can actually compress the amount of explained variation to just a few components. However, the most challenging part of PCA is interpreting the components. For our work with Python, what we're going to do is walk through an example of how to perform PCA with scikit-learn, and we'll review this sort of theory as we go along. So don't worry if you weren't 100% on the theory right now. We're going to review it as we go through the process of performing PCA with Python. What we'll also want to do is usually standardize our data by some sort of scale. We're going to cover how to do that as well in the next lecture. Since this algorithm is usually used for analysis of data and not a fully deployable model, there won't be a portfolio project for this topic. Okay, thanks everyone, and I'll see you at the next lecture.